Thank you, John. Thank you. Okay, as John pointed out, for the better part of my recent life, I've been building, in fact, better part of all my life actually, I've been building distributed systems, and more recently focusing on problems of proving out resiliency of these systems. And in a sense, that's where my entry into this story starts. So in terms of my talk, I thought I'd start off by, first of all, saying something about what chaos engineering entails, what it's about. So the term is initially coined by Netflix, and the idea is to emphasize an empirical approach to testing and monitoring distributed systems. And in defining an experiment, the idea is you'd first of all define some views of this system you have under study. You might define those views in terms of some form of monitoring metrics, be they business or whatever. And then the idea is you'll then go ahead and randomly inject faults into this system. You might kill containers, which is a traditional chaos monkey approach, or you might start changing networking behavior. Or, for myself, I'm more interested in working at the system level. So actually starting to change characteristics of function calls, be they at a system OS level or within some form of JVM, to see literally what happens. And the idea as part of the experiment is you've gone away and you defined some notion of a steady state behavior, some notion of an expected behavior. And when you see a deviation from that behavior, you have failed the experiment. And we're always interested in experimental failures. Just like with testing, any other type of testing, you're interested in the failures. The successes rarely really help you, particularly when you're trying to prove something. Okay, so the way in which I'm going to frame formalizing this is we'll end up introducing some notion. We're going to need some way of being able to define what a behavior is for a system. So I'm going to do that using a notion of a runtime monitor. And collections of runtime monitors, somehow organized together, they're going to give us the ability to then have principled experiments. Okay? And so we can then start working out whether we've got a deviation from some form of expectations. I'll introduce a notion of finite state machine. Well, state machine, to wrap these runtime monitors together. Okay, so that says a bit about chaos engineering, and hopefully, if you're also interested in building resilient systems, you're already motivated for why you have to do fault injection. If you can't do fault injection and you're not doing fault injection on your system, how can you say it's resilient? Simple as that. However, for a larger part of my life, I've also been involved with formal verification. So I'm very interested in the subject of verification. And so I think it's also interesting here in the sort of context of applications I'm building, where I'm typically wrapping code up in Docker containers and then deploying these fleets into cloud environments, to question what sort of verification practices do I need here, and do those verification practices lead me naturally to need or rely upon fault injection to prove things out properly. And of course, before we get there, one of the tenets of doing this type of stuff is you potentially apply this to production systems. However, that's not going to really be a theme for today. So, let's think about verifying software in cloud systems. Now, when you're verifying software in non-cloud environments, in one sense, you've got it easy. You have it easy because the environments in which you're verifying against they're essentially static or constrained in some way. Even some of the more interesting work done not so long ago in COC, whereby they're targeting and proving things against environments where fault injection can occur, even there, they're constrained in the type of environments they target and verify against. The problem in a cloud environment is you've typically got a highly dynamic environment, which is kind of bad, but it's even worse. You have absolutely little or no control over those environments. So verification now becomes really, really difficult. You're taking your code, which might be, for example, developed using full-blown formal methods with one set of contextual assumptions, and now you're deploying and running that code in a completely untamed, unconstrained, wild environment. You have no control as to how that code's executed whatsoever. When you start taking into account deployments into these environments, that's typically also using unverified processes. DevOps will come along and rewrite your Docker entry points without ever telling you. They'll start mapping these things to run in very strange and esoteric cluster management systems, potentially. And you'll have little or no control over that. So now we end up in a situation where the potential for some form of unanticipated failure now, instead of being remote, like up here in this world, has now become highly likely. So whether we like it or not, if we're interested in actually verifying our code, particularly if we're deploying to cloud environments, we find ourselves in a situation where we've got no choice. We have to test and embrace for failure. Right, so having motivated why we're interested in doing fault injection, having recognized that fault injection is actually central to verifying the behavior of systems within cloud environments, or cloud-like environments, let's start getting to the meat of today's talk. So what I'd like to do today is I'm going to go through a worked example in a moment of applying some fault injection. But prior to that, what I'd like to really be sort of my goal for today is to focus on how we can actually use instrumentation and fault injection in our everyday work. Now, the sort of systems, as said, that I'm going to have in mind here are all going to be Dockerized applications. Some of them might contain Scala code, some of them might not. We're talking lots of heterogeneous boundaries. We deploy them into some form of environment, and I'm then going to want to monitor and fault inject those systems. So I'm going to take a kind of a grey box view of the application. If I'm going to set up some form of experimental environment, I'm going to have some way of monitoring that deployed application so I can see what it's doing. I'll need to instrument it with sensors. And so I can fault inject. I'm going to need to have some additional instrumentation for injecting faults into that system. And sometimes the faults might just be regular data. Sometimes the faults might be real faults where I'm messing around with nicks and things like that. Now, clearly, in doing that, I'm writing code which has lots of side effects. One can't, to a degree, can't escape that. So, the library code that I've been working on for a while now, it's an open source Scala library, still under development, and it'll optionally deploy, orchestrate, and instrument Docker container code. If I'm going to have any form of instrumentation layers there within the Docker container, be they sensors or injection points, I'm going to have to add additional layers so I can get that instrumentation code in place. But what I don't want to do, I want to be able to take production containers and not modify them. I accept I might have to add instrumentation layers to them, but I don't want to physically modify the code that's in that container. Yeah? I don't want to go too far away from a production-like environment. I'd like, when I'm doing this, to be agnostic of the deployment environment, within reason. The behavioral and runtime properties that I specify, I really do need them to be composable. I want them to be reusable. I want to be able to build big things out of little things. And experiments I define for these fault injections, I really do want them to be reusable. Because showing that something can